Now let us see Cauchy residue theorem. The statement of this theorem is if f of z be an analytic function at all points inside on the simple closed curve C except for a finite number of isolated singular points, that is z1, z2, etc. zn inside the closed curve C. Then integral over C f of z dz is defined as 2 pi I into sum of all residues at their poles. That is, here isolated singularity is otherwise called as poles here. Suppose we consider, that is, in a simple closed curve C, if there are n number of singular points, that is z1, z2, z3, etc., zn. Okay, if these are all the singular points inside the closed curve C, then how to calculate or how to evaluate the integral using the residue theorem. So integration f of z dz is equal to 2 pi I into sum of residue, that is at each poles we have to calculate the residue and then we have to add it. So that will give you the value of this integral f of z. So this is the statement of Cauchy residue theorem. So we can see some example. First example is evaluate integral over C z square by z plus 1 into z minus 1 whole square into dz, where C is modulus of z equal to 2. That is, modulus of z equal to 2 is a circle with center, origin and radius 2. So we have to evaluate this integral for this closed curve C using Cauchy residue theorem. So using Cauchy residue theorem we have to evaluate it. Now let us see how to evaluate this. So here the function is f of z is equal to z square divided by z plus 1 into z minus 1 whole square. So this is the function given. We have to evaluate this for the simple closed curve C, where this C is modulus of z equal to 2. So what do you mean by modulus of z equal to 2? It is a circle with center, origin and radius 2. That is, z is nothing but x plus iy. We know the complex variable x plus iy, which is equal to 2. So modulus of a complex number, how to write it? Square root of x square plus y square, modulus of a complex number. So this is equal to 2. To remove the square root, we can write it as x square plus y square is equal to 2 square. So this is nothing but it is a circle with center, origin and radius is 2. Right? So whenever you come across modulus of z, means it is a circle with center, origin and radius is 2. If it is 2 means radius is 2. If it is 1 means radius is 1. If it is a means in general we can remember modulus of z equal to a means it is a circle with center, origin and radius a. So here it is a circle with center, origin and radius 2. So now we have to identify the singular point. So what are the singular point? As usual, I ask you to equate the denominator to find the singular point. So z equal to minus 1 from the first term. From the second term it will be plus 1. So both are called as singular points, or we can call it as poles here. Okay. So while talking about poles, we are having simple pole as well as pole of order m. So here if you notice z plus 1 occurs only one time, we can say that z is equal to minus 1 is a simple pole and z is equal to plus 1, that is z minus 1 whole square we are having. So this is called as, it is a pole of order 2, or sometimes it is called as double pole. If it is a pole of order 2 means, otherwise it is called as double pole. So now we have to find out the residue at both the poles. Okay, so this is one pole, another pole is z equal to 1. So at these two poles we have to find out residue. So we will be getting two residues. Let us name it as R1 and R2. So first case, it is a simple pole. So already we know that for simple pole we know the formula. So directly I am writing here. So this is equal to limit z tends to minus 1. So it should be z plus 1 into f of z. F of z is what? Z square by z plus 1 into z minus 1 whole square. So this and this get cancelled. Now applying the limit here, z tends to minus 1. So minus 1 whole square is plus 1 divided by minus 1 is minus 2 the whole square. So it will be 1 by 4. Clear? So this is R1. Next we have to find out the residue for z is equal to 1, that we can consider to be R2. So now R2, let it be residue of f of z at z is equal to plus 1, which is equal to limit z tends to 1. Here it is a pole of order 2. So here it should be 1 by 1 factorial d by dz of z minus 1 whole square into f of z. F of z is z square by z plus 1 into z minus 1 whole square. So now what happened here? This and this get cancelled. So that we have to calculate it d by dz of z square by z plus 1. Now we have to apply u by v rule. Okay, here we have to apply u by v rule for differentiation. So if we differentiate it using u by v rule, so already we know that what is the formula for u by v rule is what? V into u dash minus u into v dash divided by v square. So using this formula, if we differentiate it, we will get the term z square plus 2z divided by z plus 1 the whole square. So now if we put the limits here, z equal to 1, finally we will get the answer as 3 by 4. So this is the second residue. Okay, now we have to evaluate. Now we have to evaluate the function f of z dz, which is equal to, the given question is z square by z plus 1 into z minus 1 whole square dz is equal to what? According to Cauchy residue theorem, 2 pi I into sum of residues. Sum of residues means here we are having two residues R1 and R2, so that we can add R1 and R2. So this is equal to 2 pi I into first residue answer is 1 by 4, second residue is 3 by 4. So adding it, it will be 4 by 4 is again 1. So the final answer is 2 pi I. So this is the answer for the given integration z square by z plus 1 into z minus 1 whole square into dz. Now let us see this example. Integral over c z minus 1 by z square plus 2z plus 5 dz, where c is the circle, modulus of z plus 1 plus I is equal to 2 using Cauchy residue theorem. So we have to evaluate it. So now if we see the circle, that is the curve C is given by modulus of z plus 1 plus I is equal to 2. So already I told you that modulus of z equal to A means it is a circle with center, origin and radius A. But here we have to check the circle, what is the center and radius of the radius is obviously 2 here. But what about the center of the circle? That we have to check here. So let us check that one. So already z can be replaced as x plus iy. Apart from that, 1 we are having and then I we are having. So modulus of this is equal to 2 is given. So now you collect the real part separately. So x plus 1 are the real part and imaginary part the term containing I. So y plus 1 again. So modulus of this is equal to 2. Now if we see, this is the complex number. So taking modulus to this and taking squaring on both sides, we can write x plus 1 whole square plus y plus 1 whole square is equal to 2 square. So if we see this equation, this is equation of a circle with center minus 1 comma minus 1 and radius is 2. So we have to consider a circle with center -1 and -1 and radius is 2, and then we have to check the singular point whether it lies inside or outside the circle. So here first let us identify the singular point. So to identify the singular point we have to equate the denominator to 0. So here if we equate the denominators to 0, it is a quadratic equation, so it has two roots. So now here it is not easy to factorize this. So as usual we can use a formula minus b plus or minus root of b square minus 4ac formula. So here it should be minus b plus or minus root of b square is 4 minus 2ac. So 2ac is 4ac. 4ac is 20 here divided by 2a. So this is equal to, we will get minus 1 plus or minus 2i on simplification, which means that minus I minus 2i and minus I plus 2i both are poles and both are called as simple poles. If we write it in a factorization form, it will be of power 1, so we are calling it as simple pole. And if we have to check whether these poles lies inside the circle or outside it. So before checking that, we can represent this complex numbers as coordinate point, that is we can write minus 1 minus 2i as minus 1 comma minus 2, that is x takes the value minus 1, y takes the value minus 2. Similarly here this number can be written as minus 1 comma plus 2. So now we have to check these points lies inside or outside this circle C. Okay, so for that first we have to draw the circle. So here if we see the, if we consider this is to be the origin, minus 1 comma minus 1 means let us take this point. This is minus 1 comma minus 1 and it is of radius 2. So consider this is to be the center and radius 2 means approximately, let us draw like this, right? So we have to consider a circle like this. So if we consider a circle like this, now we have to check whether minus 1 and minus 2, minus 1 and plus 2 where it lies. So minus 1 comma minus 2 means this is the point minus 1 comma minus 2. So minus 1 comma minus 2. Where is minus 1 comma plus 2? Minus 1 is this, plus 2 will be here. This is minus 1, plus 2 will be here. Okay, so this is the point minus 1 comma plus 2. So which out of these two poles only one pole lies inside, another pole lies outside. Okay, so here we can conclude that z is equal to this alone lies inside, this lies outside. Okay, we have to calculate the residue only for the poles which lies inside the given circle. So z equal to 1, that is 1 minus 2i, okay, is a simple pole lies inside C. Okay, C is the circle which is given here. Okay, inside C. Now it's enough to find out the residue only at this particular pole alone. No need to find out for this particular pole. Suppose if you have the circle, some other circle is given where both the poles lies inside, means we have to calculate the residue for both the poles and add it together and apply Cauchy residue theorem. We will be getting the answer to this integration. So now here only one pole lying inside the circle C. So we have to find only the residue for this pole alone, that is minus 1 minus 2i. Now the given pole is a simple pole f of z at z is equal to minus 1 minus 2i is the simple pole. We can apply it in the formula minus 1 minus 2i, and here the function is and while writing it as a factor we have to write it like this. Clear? That is z minus a. Minus of minus will become plus. So we have written like this into f of z. F of z is what? This is the function. And here we can write it in the factorized form, because two roots we are having, minus 1 minus 2i, right? So while calculating like this, here this and this get cancelled. To the remaining term, if we substitute z equal to minus 1 minus 2i in this function, we will get the answer as 1 minus plus I divided by 2i. So this is the residue for the pole minus 1 minus 2i. Okay, so that we have to calculate the integration, that is z minus 1 dz by z square plus 2z plus 5 is equal to 2 pi I into sum of the residue. Here only one residue we are having, we can write that residue. So here we can cancel this 2i 2i. So finally the answer is 1 plus I into pi. Okay. So this is the value of the integration for the given curve, given simple closed curve C. Okay. Here it should be z plus 1. Okay, this is the way we have to evaluate the integral based on the poles lying inside or outside the closed curve C.